The topic of radioactive decay needs to begin with a nucleus. Now recall that the nucleus of an atom is comprised of protons, which I'm using blue circles for the nucleus, or for the protons. And so let's label that. And the little gold-colored circles are the neutrons. And protons have a positive charge. Neutrons are electrically neutral. They do not have a charge, but they help hold the nucleus together. Now, because protons having positive charge, and because like charges repel, the more protons you have in a nucleus, the more unstable that nucleus is, because those protons want to push against each other and break apart. So when radioactive decay occurs, what's happening is part of that nucleus breaks off. Now, there are different kinds of radioactive decay. So what changes is what is shot off. So sometimes what is shot off is 2 protons and 2 neutrons. So in this case, we have in our original nucleus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons. So we've just lost 2 protons. So we're going to have 8 protons left. And our original nucleus had 9 neutrons, so we're going to have 7 neutrons left. So this would be one example of radioactive decay, where we've lost what's called an alpha particle. It's really the nucleus of a helium atom, and the rest of the nucleus remains. And so what remains is stable. So we have gone from being unstable to stable by losing part of that nucleus. Now, other possibilities are it would lose a single proton, or it might lose a single neutron. It really just depends upon the original nucleus. So that's what the decay process is. It's going from an unstable nucleus to a stable nucleus. So the next step is, after we've determined that a particular element is unstable and does undergo radioactive decay, is how long will it take before that atom decays? And that is indicated by what's called half-life. So our terminology, the parent atoms are the unstable original nuclei or atoms, and the daughters are what it decays into and is what is stable. Now, half-life is a statistical process, and by that it means that if you have a large enough original sample, in the time indicated by the half-life, statistically, half of your parents will have decayed. So in our example here, we have 24 parent atoms and 0 daughter atoms as our starting point. So what we're going to look at is, what should we see after one half-life? Well, by the definition of half-life, we're going to lose half of our parents. So now we're down to 12 parent atoms, and we are going to gain 12 daughter atoms. So however many parents we lose, that is however many daughters we gain. So that's one half-life later. If we wait a second half-life, we're going to lose half of our 12 parents. So now we're going to be down to 6 parent atoms, and we're going to gain another 6 daughters. So 2 half-lives later, we're down to a fourth of our original parents, and all those other parent atoms have been converted into daughter atoms. Another half-life, we're going to lose another half of our parents. We're going to be down to 3 parent atoms, and our daughters are going to gain another 3. And so the process continues on. What this allows us to do is, in a laboratory, we can measure how long it takes this process to take for our elements to decay. So we know the values of the half-life. So then, if we have a rock sample, we can look to see what is the ratio of daughter elements to parents. So in this example, there's 3 times as many daughters as parents. Well, that's 2 half-lives later. So if we know the value of the half-life, multiply by 2, we know how old our material is. And this is how we determine the age of rock samples. So rocks brought back from the moon have ages ranging from 3.3 billion years old to about 4.4 billion years old. So that tells us something about how old the moon is. Same sort of thing for meteorites or rocks from the earth. This is the process we use to determine the age of our samples.